Well, welcome. In this video, we're going to be looking at the inverse cosine function. Now, if you recall for inverses, when we identify an inverse, we use that exponent -1 to identify the inverse. For example, on the far left there, you can see that we have f to the negative first power of x. That, as you may recall, is how we identify the inverse of a function. Well, when we talk about the inverse then of the cosine function, we're going to write it out in a similar manner. We're going to use the cosine and then a -1 exponent to represent the inverse of the cosine function. Now, what is the inverse of the cosine function? Well, the way that you can think of it is that the inverse of the cosine function is the number whose cosine is whatever x might be. So that's what you ask yourself in your head. What number has the cosine of whatever x is? And in a little bit, we'll look at an example where that'll make more sense. Now, the other way that we identify the inverse cosine is by what's called the arc cosine. You don't see that as often. Usually I refer to it as the inverse cosine with the -1 as your exponent. That's how I will refer to it. But if you ever see arc cosine, it means the same as the inverse of the cosine function. Now, what is the graph of the inverse cosine function look like? Well, that's what we're going to look at now. So over here we have, if you recall, the cosine function starts where x is 1, and then it goes down, and you can see that the graph would keep going in both directions. Now, that's the whole function for the cosine graph. Now, if I were to, or if you remember from previous chapters in advanced algebra, we talked about inverses. We talked about even inverses in the past this year. So you want to make sure that you remember some properties of inverses. Remember that inverses are reflected over the line y equals x. But also remember that we have what's called the horizontal line test. Now, the vertical line test is where if we're looking at a graph, we use the vertical line test to see if that graph is a function. So on the far left there with that cosine function, we can see that it would pass the vertical line test. Even if you extended it out in both directions, it would pass the vertical line test. So that graph is a function. Now, if I left that cosine function open where it went infinitely in both directions, it would fail the horizontal line test, meaning that if that was the case, the inverse would not be a function. However, if I restrict the domain, if we restrict the domain, put limits on it to go from 0 to pi, or from 0 to 180 degrees, that's what they've done here on the far left, then that passes the horizontal line test. So not only does that graph on the far left there, does it pass the vertical line test, but it also passes the horizontal line test, meaning both that graph and its inverse would be a function. So that's what we're going to do. We're going to limit the domain, so in that way the inverse of the cosine function would also be a function with those restrictions. Now, like I said, if you look now here closest to me, we have the graph of that cosine function, and you see that in red we have what would be the inverse of the cosine function graphed. Now, recall that the inverse is a reflection of the line y equals x, and that's what it's showing us here, that it's reflected over that line, y equals x. And also remember for the inverse that the domain and range are switched. So originally the domain for our cosine function with its limitations would go from 0 to pi, or from 0 to 180 degrees. Well, that domain would now be the range for the inverse of the cosine function. So as you look here, as you look at the y-axis, you can see that the y-axis is also in radians, and it's going from 0 to pi, and that's where the range is ending there. And remember that the range for our original function would be from -1 to 1. But that range for our original function is now going to be the domain for the inverse. So as you can see here, our domain is going from -1 to 1. So that's our inverse. So the reason why that's so important is that gives us a very important piece of the inverse cosine function. And that's that the inverse cosine function is always going to be dealing with values between 0 and pi, or 0 to 180 degrees. So here's what you're going to do. We're going to look at this example here, and we're going to use this concept that's highlighted in yellow that we just talked about with, and again, the reason why we're dealing with 0 to 180 degrees is because we have to restrict the domain for the cosine function, so its inverse will also be a function. So we're going to use that information now to be able to work out these examples and some other examples. So let's look at these examples now. So let's look at this one. So it says to evaluate this without a calculator. Now remember from the beginning of our lesson, we said that the cosine function is, the way that we want to think of it is it's always going to be, whoops, the number, I can't spell, the number whose cosine is square root of 3 over 2. That's the way that we need to think of this. So with the inverse cosine, we're trying to think of the number or the angle whose cosine is the square root of 3 over 2. Well, remember what we just talked about, that it's got to be between 0 and 180 degrees. Well, if you think about between 0 and 180, square root of 3 over 2 is positive in quadrant 1. So in quadrant 1, square root of 3 over 2 is going to be where we're dealing with a 30-degree angle. So the cosine of 30 degrees is the square root of 3 over 2. So the inverse cosine of square root of 3 over 2 happens at 30 degrees. Now that would be my answer. However, they say to write your answer in radians. So recall from the previous chapter that we would multiply this by pi over 180. And if you do that, we can see that it's divisible by 10. And 3 pi over 18 reduces to be pi over 6. So that would be our answer in radians. So why don't you guys try this next one on your own? So why don't you pause the video and hit play when you're ready to check to see if you have the correct answer. Okay, so you should have gotten that the cosine of -1, or the inverse cosine of -1/2 is 120 degrees. Since it's a -1/2, it's going to be in quadrant 2. So when you focus on quadrant 2, when the cosine is -1/2, it happens at 120 degrees. So that would be our answer. But then they say to write it in radians, so we're going to multiply that by pi over 180, and so you end up getting 2 pi over 3. So you should have gotten 2 pi over 3 radians as your answer. Now let's look at the difference between that question and the next set of questions. -0.333 and 0.99426 are not ones that we would have memorized, so these are going to be ones we would do on our calculator. Now, how would we do this on our calculator? Well, if you use your calculator, if you go to your calculator, what we're going to do is, if you remember from the trig button, we have all these options, and one of those is the inverse cosine. So if I select that, and if we want to take the inverse cosine of -0.33333, hit enter, and we get 109.47 or 109.5 degrees. And that would be our answer. It's 109.5 degrees. So we're not going to do the next one because it's just as easy as just plugging that in your calculator. Now before we go on to the next paragraph, I want to talk about something important to understand about the inverse cosine function. And that's this. That's that the inverse cosine and the cosine of an angle undo each other. So the inverse cosine and the cosine, they undo each other. So that means that if we take the inverse cosine of the cosine of an angle, your answer is just going to be the angle. So if you remember from what we did in the previous lesson with our sine, cosine, and tangent, those trigonometric ratios, that we would use those trigonometric ratios to find the measure of a missing side for a right triangle. We can use the inverse cosine to find the measure of a missing angle for a right triangle. So let's look at how we can use that and what we just talked about here in purple to answer this story problem. So here it says the Landsat 7 satellite orbits Earth at an altitude of 705 kilometers, which is 438 miles above the equator. It can only see a portion of Earth's surface at any given time. Imagine looking at a cross-section of the satellite and Earth as shown below it to the right. So that's what they're showing down here. Point C is the center of the Earth. H is a point on the horizon circle, so that's over here. And S is the location of the satellite. Let the angle equal measure of angle HCS. So HCS would be this angle here. The altitude A of the satellite is the distance in kilometers of the satellite above Earth, which they told us that's 705 kilometers. Notice that angle CHS is a right angle. So even though they don't say that, that would be a right angle because it's tangent to a circle is perpendicular to the point of tangency. So that's they're just showing us here that they're telling us that that would be a right angle. So we want to write a formula for theta in terms of R and A. So if I look at this right triangle that we have here, down in the bottom right, R would be the adjacent leg to this angle, And this side here, CS, would be the hypotenuse. So to find the measure of angle theta, what we would do is we would say the cosine of theta equals the adjacent leg over the hypotenuse. Now in this case, my adjacent leg is r. My hypotenuse is not just r, it's not just a, but it's r plus a together, because r is, remember this is a cross section of the Earth, so r is representing the radius of the Earth, a is the distance from the surface of the Earth to the satellite. So the distance from the center of the Earth to the satellite would be the radius plus the altitude. Now this gives us our ratio, so the cosine of theta equals r divided by r plus a. But what we want is a formula for theta. So I want to get rid of the cosine. So what I'm not going to divide both sides by cosine. I've seen people do that. That's wrong. We want to take, because what we just talked about a second ago is that the inverse cosine undoes the cosine. So I'm going to take the inverse cosine of both sides. That leaves us, which is theta on the left equals the inverse cosine of r divided by r plus a. That would be our formula. So now when it says the radius of Earth is about 6,378 kilometers to the nearest degree, what is theta? Well, we're just going to plug this in our calculators. Now it's important to make sure that you do this on your calculator correctly, so I'm going to show you a little trick that's handy and good to know about. Oops, it's 7:05, not 7:07. So I'm going to show you how to do this on your calculators. So again, we would go to the inverse cosine. Now I'm going to have this big fraction. Now I want to make sure that I put this in correctly, because if I don't put it in correctly, your calculator is going to give you the wrong answer. So we want to hit control divide so we get this fraction bar. So now I can type the 6,378 in the numerator and put the 6,378 plus 705 in the denominator. So now that's typed in exactly how I have it in my worksheet. So now if I hit enter, I get about 26 degrees if we round that to the nearest degree. Because if I hadn't done it that way, if I would have just typed it in my calculator as a 6,378 divided by 6,378 plus 705, the calculator is only going to take and divide these two pieces because it's going to follow order of operations, and then it's going to add 705. So that's why you want to use that fraction bar, so that way your calculator knows the proper order to do it in. So we get 26 degrees as your answer. Now I'm going to have you guys try this next one on your own, but I'm going to help you first get it started because it's a little bit trickier. So this is a prop of a proscenium on the back of a, to prop up a proscenium on the back of a stage, you have a 9-foot, 6-inch board whose foot is 5 feet 3 inches from the back of the proscenium. What is the measure of the acute angle formed by the board and the floor? Okay, so this would be our board. This is the distance it is away from that proscenium. So now they say that this is 9 feet 6 inches, and this is 5 feet 3 inches. Now right now we have mixed units. We have feet and inches being used here. We want to convert these either all to be in feet or all to be in inches. Now if we convert this to feet, which is what we're going to do here, we do not just simply state that this is, don't just write this as, oh, it's 9.6 because it's 9 feet 6 inches. That is wrong. So please do not do that. It is going to be 9 in a decimal, but 6 inches is half of a foot. 6 divided by 12 would be 0.5. So this would be 9.5 feet. So even with this base, it's not 5.3. 3 inches is 3/12 of a foot, and 3/12 reduces to 1/4, or 0.25. So this will use as 5.25. So even though 5.3 and 9.6 would be close, it would be inaccurate. So if you do that, you're going to get the wrong answer. So please make sure you know how to convert feet and inches into just feet. Okay, so now I want you guys to figure out what the measure of that angle is going to be, using the fact that our base, our adjacent leg, is 5.25 feet, and our hypotenuse is 9.5 feet. So why don't you guys go ahead and work this one out on your own. And so pause the video and hit play when you're ready to check your answer. Okay, let's check to see how you did. You should have gotten 56.5 degrees. The way that you do that is you set this up saying the cosine of theta is equal to the adjacent leg over the hypotenuse, so 5.25 over 9.5,
Take the inverse cosine of that ratio to find the measure of the angle, and you get 56.5 degrees. So that's it. That's all we're going to do with the inverse cosine function. So hopefully that makes sense to you, and good luck now as you work on your assignment.